Euclidean space, so it was a bit limited in that sense. And so the approach they take is to essentially divide the configuration space into these convex subspaces, and then they're solving convex optimization problems on the convex subspaces. And so then they can solve this shortest path problem over these convex subspaces and then use that to find the global solution to the non-convex optimization problem. And yeah, they make some claims that their formulation has the same guarantees as the formulation on the Euclidean space, and they can solve these very challenging problems.
Oh wait, sorry.
Yeah.
Could you share your screen to the Zoom?
Oh, yes.
Oh. There you go.
Okay. And yeah, they evaluate this on a few different robot experiments that I will talk about in a second. Okay, so why this paper? If you were at me or Avi's last reading group presentations, we've been working on this idea of consensus ADMM. So the idea is kind of taking this multi-agent approach to trajectory optimization to do more exploration and not get stuck in local minima. And so there were some relationships between that problem and the problems addressed in this paper. And specifically, I've been trying to solve a problem like this very simple little maze on the left-hand side. The figure on the right-hand side is from the other paper by Russ Tiedrich's group that this work is based off. And so I've been trying to kind of build up to a more complex situation like they have in their paper. So I wanted to kind of dive into this paper. This is a shameless plug for my first ever paper that I wrote in 2021. It's also my most cited paper, unfortunately. And true, but like by far. Anyway, so basically this is using a Kalman filter that worked on matrix Lie groups, which are like these manifold Riemannian manifold objects, and basically showing that you can get improved performance just by like putting your state into this framework of a manifold, which is kind of cool because it's like this very simple change and you get much better performance overall. Okay, so the problem that they're addressing here, like I said, is that motion planning in high dimensions is hard. I talked about this before, but sampling-based methods and trajectory optimizers both have issues and struggle in these large problems. And in addition to this, real robot spaces are manifolds. So for example, if you have any kind of joint that rotates, that is a manifold. Anything that moves in three-dimensional space is working on a manifold. Okay, so now I'm going to talk about their previous paper because it's very important to the current paper, and hopefully reading the paper wasn't too confusing without reading this previous paper, but yeah, okay, so this is a science robotics paper from 2023. It was this really big paper. That's where the maze figure from a couple slides ago came from. But essentially what they do is they show that if they have this space, like the box on the left-hand side here, here the red region is an obstacle. And so the space that the robot can go in is non-convex because of this obstacle. But they show that they can split up the space into some convex subsets, and then solve trajectory optimization problems kind of within each of these spaces. And they form a graph that shows like the connectedness of these spaces. So for example, in this case, you can go from the start, which is this sigma, through 1, 2, 4, 5, or you can go from 1, 3 to 5. And then they're kind of solving two problems simultaneously, which is a shortest path through the graph, with like weighted by the length of the segment that goes in that convex subset. And they're also solving a trajectory optimization problem within each of the convex subsets. So basically they're trying to figure out these segments and also how the segments fit together. So if you're going to go, you know, down and around the obstacle or above and to the right.
Good question.
Yes.
Difficult or hard, or how hard or easy is it to get those convex subsets? Like given any, environment, geometry?
I think getting the subsets, they don't really talk about that in any of these papers as far as I can see. I think that problem is not necessarily super hard, especially if you have like polytope obstacles like this. I guess like if your obstacle was a circle, then you'd have like infinitely many sets to be able to do this. But I guess in general, they just assume that it can be done pretty easily. And in the examples later on, I can touch on that, but basically they so they have an experiment where they are doing like a cup reorganization. So they have these shelves and they're trying to place the cups. They have like 3 different shelves and 3 different color cups, and they're trying to place like all the red cups on one shelf, all the yellow cups on another shelf. And they talk about how they break up the space in terms of like the configurations of the robot. So the convex sets are like the robot reaching into one of the areas or the robot reaching into another one. So they seem to have these very like geometry based ways of splitting up the space.
I see. So there's like, you could just like in that figure, you could just like randomly cut it up into these convex subsets. But you're saying
Yeah.
you can be a bit more intentional about how you break it up. Like Q1 could represent, the robot in this configuration.
Yeah. Yeah, I think so. Yeah, like if this was, yeah, I guess like in this case, you could say like, oh, being to the left of the obstacle, being to the right. That's not really what these are doing, but
Would work if the obstacle was dynamic? Could you like resolve it pretty quickly online if
I don't know. That's a good question. Yeah, they talk about computation time for the actual algorithm, but I don't think they include breaking up the space
is the
into these
actual problem
sets.
practical? So do you solve like all of those trajectory optimization problems, all of them?
All simultaneously, yeah.
Simultaneously?
Yeah.
And then the graph problem? Or-
That's also being done simultaneously. I think my next slide is on that. So yeah, essentially they're trying to solve this problem of, like I said, finding which path to take and also minimizing the length of the path. And so those 2 problems influence each other. They're trying to find which of the paths will have the shortest length. And so they pose that problem here in this very general way where they're trying to minimize, here L is the path length, P is the set of all paths through the graph. XV is like one of the convex sets. I guess they're Q in this figure, and XV here. And so they're basically just minimizing the length of a path such that the path is one of the possible paths. XVs are in each of these sets. And I guess XU, XV is in the set of edges. But this problem is very hard to solve. So you can kind of solve this more easily in one of 2 ways. You can fix the path that you're going to take, and then it's just a trajectory optimization problem. You can fix the vertices, and then it's just a shortest path through a graph problem. But if you want to figure out like where to place those vertices and also which path to take, it becomes really hard. And so it's an NP hard problem. And so they come up with this mixed integer program that can solve this problem. I'm not going to go through this, but basically they're just like, it's a mixed integer program. And I think you kind of see how they could do that. Like you can either turn the segments on or off and then solve that problem. And there's some pretty good mixed integer program solvers these days that are pretty quick, like Gurobi. And then they relax it, but that also is not super important. But this is all the from the prior work on doing this in Euclidean space. And then in that science robotics paper, I think I said it was, oh yeah, science robotics paper, they have all these examples. So this is one example where they say that they can minimize different objectives. So they can minimize length, like path length, minimize time subject to some smoothing constraints, and they show that they can find all these different solutions, whereas like trajectory optimization would just find whichever solution the initialization is closest to.
Another highest level question. I can see how this would make solving the individual optimization problems easier because you get guarantees because the sets are convex. But how does this actually help you with the cursive dimensionality? Do you need to sample less points after chopping it up?
So they don't need to sample points. I guess you would need more convex subspaces in a higher dimensional space.
So
But
they're not sampling random points in each convex subspace.
correct. Yeah, so within, yeah. So they're basically doing trajectory optimization over each of these subspaces rather than just like sending out a bunch of particles, but they're kind of taking from the sampling based literature and like sending out these like convex spaces, I guess. Convex subspaces.
Yeah.
In a sense. Yeah, so basically they show that they can find the optimal solution amongst like a non-convex landscape. And then they show this pretty impressive looking example where they find a trajectory through this maze.
How fast do they find it?
I don't have a number on that, but it's probably in the paper somewhere.
Why did you say? You or the.
Oh, this is them. This is just a figure from their paper. I think they're just showing that they smoothed it with some additional constraints on the right-hand side here. But yeah, they can basically like impose additional constraints. Do you have the runtime?
Yeah, seconds, like 25 seconds or something.
But I don't
Is that
know.
for
There's
this?
There's one that's for results.
It's the new paper. I don't know what the
Yeah.
times mean.
Yeah, I
but
can
there's
find the old paper. If you Google Rust,
seconds for something.
is that from this paper?
It's the one you shared.
Yeah, that's for the like pick and place problem.
Okay.
Let me look for the maze.
Okay, but it's like.
It's pretty quick.
Yeah, it seems like it's pretty,
For something like that, it's pretty fast.
it's pretty
Yeah.
fast.
I think. I couldn't solve that maze in 20
Yeah.
seconds.
The Isaac baseline.
No. Took like 10 minutes maybe.
Bro, I don't know if I
Hour.
would finish it. I would give up.
It looks like for that one, the runtime was maybe 50 seconds.
For the maze?
Yeah. Wait, offline runtime. Okay. Offline runtime 31 seconds.
What hardware
Here,
is that?
this is I don't know. Reading the paper live right now.
Sure.
But yeah, here, this is there.
Yeah.
Yeah, that one.
This is the previous paper.
Yeah,
What's
it's
previous
the
paper?
It's called Motion Planning Around Obstacles with Convex Optimization. It's the same first author.
if you look up Rust Cedric maze, it comes up. It's usually what I do. Yeah, so pretty impressive.
I'm glad to see he's still doing non-learning stuff.
Yeah,
Although
only
this is a
person in the
little
world.
harder.
It's actually often all in for like large behavior models.
Oh yeah.
Okay, so they solved all these cool problems, very impressive. But this paper was motivated by this problem. It's a Willow Garage PR2 motion planning problem. So they have two robots that each have two arms and they're trying to place stuff on the shelves. And because the robots are moving in two-dimensional space and have these arms, they can no longer use this graph of convex sets, they call it, that only works in Euclidean space. So that is the motivation for this work. A bit of background. So a Riemannian manifold is a smooth manifold. So it can be like any kind of angles that exist on like the surface of a sphere are a manifold, and that is yeah, basically like any kind of angles or anything that doesn't just like move in linear space. So because an angle can like, you can move 360 degrees and get back to the same position, you're not in Euclidean space because you're not like moving along lines. That was a really bad explanation of manifolds, but you get it. Okay, so there is this concept of geodesics in manifolds, and a geodesic is a curve that represents the locally shortest path between 2 points. So for example, on a sphere, if you draw 2 points on a sphere, the shortest path that connects them is if you draw a circle that has the same radius as the sphere but goes through those 2 points. So that's the geodesic curve. Wikipedia also has this interesting definition that if an insect is placed on the surface and continuously walks forward, then it'll trace out a geodesic. So if it's walking from like one point to another, that is apparently the geodesic. I'm not sure why insects are chosen to be are necessarily optimal, but
Like facing the wrong way.
I guess like if it's trying to walk like forward to the point, I don't know. I
Maybe
guess
it's
it depends on your
insects
definition of forward.
operate
Insects know this.
like
It's not like
energy
laundry.
to propel.
Yeah. But I think it gives you an idea. Like it's kind of like forward in this like weird curved space. And in a general manifold, there isn't a unique geodesic between 2 points. And then there's this concept of curvature on a manifold. So there can be positive curvature. So for example, a sphere is what represents like an attitude in 3 dimensions. So like a ball joint, for example, would operate on a sphere. And it has positive curvature. And then there's zero curvature, which like is kind of, it only applies to very specific systems. So it's like a 2D joint has zero curvature, and then there's negative curvature. I don't have an example of that. But spoiler, they show that their algorithm only actually works in zero curvature spaces. So it doesn't work, for example, on like a ball joint or like a quad rotor that moves in 3-dimensional space.
Maybe also something to note, like our knowledge of that angles of a triangle sum up to, was it 180?
Yeah.
Apply.
Yeah, I guess that's what this figure is trying to show, is that like in a manifold with flat curvature, the angles of a triangle still add up to 180. But if you are in a positive curvature space, then it adds up to more than 180, and in a negative curvature space, it adds up to less than 180. And so like everything kind of breaks down.
Is it kind of
in
like
those
a feature
spaces.
work or possibility result? It just-
They show that it just results in non-convexity.
So I have a question on that.
Yeah.
So in the paper, it says that they have a proof that this is like you can't do what they're doing for positive curvature, but they don't mention negative curvature.
Yeah, they don't talk about negative curvature anywhere in the paper. I would imagine it's the same
Okay.
because, yeah, I can't imagine they would. Basically, the problem is that like geodesics are non-unique, and so, like the concept of, I think this is maybe my next slide, but the concept of like a set is convex if you can draw 2 points and the line between it is always inside that set. If it's I think the curvature either positive, I guess negative would like push you further into that set. So
Right.
but positive, like your line can get kind of pushed outside of the set. And so you end up with non-convexity.
Okay.
I don't know. But yeah, I've also wondered why they didn't address that anywhere in the paper. Okay. So they introduce this concept of strong geodesic convexity, and this is not a general definition. Like the other papers use different definitions of this. But this is kind of equivalent to what I just mentioned, that a set in Euclidean space is convex if you can choose any 2 points in that set and the line between them remains in that set. And so this is kind of a similar concept that a subset U, which is a subset of some manifold M, is geodesically convex if for any 2 points chosen in U, there's a unique length minimizing geodesic connecting those 2 points. So you can connect those 2 points. It's also length minimizing, which I think is part of the issue from if you have a curved manifold, that it can kind of like curve your line in different ways and get you the same distance between the 2 points. And it's entirely contained in U. Okay, and then they also have this other definition, which looks very similar to Jensen's inequality, but saying that a set is geodesically convex if this inequality holds. All right. So the approach they take is to solve this optimization problem. So this is a shortest path problem between P and Q. So they're solving the argmin of some objective L, which is a distance metric between P and Q. And it has this form in the box. So it's this integral from A to B of the inner product of these segments.
When you say what's lambda? So,
Gamma.
yeah, sorry.
It's
That's the parameterized path.
yeah.
I think of the cost there, like the
This.
length of L.
Yeah.
That's just like the integral of your path,
Mhm.
that it's weighted by some metric.
Yeah.
Because you do an inner product. Is it inner product? No.
So
Like,
M is a projection onto the manifold, I believe.
yeah, like I computed actually in my first paper, I
Okay.
computed geodesics. But basically you can think of that, maybe it's M or some other basically matrix that is basically weighting your distances. So it's going to be gamma transpose M gamma, right? Because if that matrix was just the identity, then you're just computing distance squared.
Mhm.
But then you are weighing it, or adding some weighting according defined by your manifold. So it's like a weighted distance
Yeah.
computation. At least how I interpreted it back then.
Yeah, I think it would essentially be what would tell you that, like, so if you had your angles going from like 0 to 2 pi, it would say that like 0.001 is very close to 6 point whatever, a little bit less than 2 pi is, right? Like it would kind of do that mapping sort of intrinsically.
I
Okay.
did it in like, so I computed geodesics in the context of contraction metrics. I don't know if any of you have seen this. This is like a generalization to like Lyapunov analysis, but so I never thought about it in angles. I don't know, think about angles a lot in my work, so I don't really have great intuition there. But you can just think of that an integral as just distance of the geodesic.
Yeah.
Like that distance is weighted by something.
Yeah. So anyway, this ends up being some like path length
Mhm.
through your manifold. And here gamma is basically the geodesic. So it's the it basically maps like 0 to 1 to your 0 to 1 to your manifold, I think. And it's in some set of all possible like paths through your space. And then yeah, it has initial value at P, final value at Q. Okay, so basically the formulation is quite similar to this figure that's in Euclidean space, but on a manifold. So each vertex has a corresponding convex or G-convex here, geodesically-convex subset that they call YV of the manifold. And each edge is assigned some cost function, which also must be convex. So it's a distance function, so it generally is just convex, or you can choose it to be convex. And yeah, again, convexity here is now in this, like, with respect to the manifold. So it's this, like, geodesic convexity. Yeah, so then they say that given source and target vertices, P and Q, a path pi is a set of vertices. So basically they're splitting up the space into these individual vertices where the vertices are in each of the subsets, which just allows them to solve these convex optimization problems with respect to each of the sets, essentially. And then they can compute the path length in this way. And basically what they come up with is this is intractable. Shocker. And so they just kind of end up projecting the problem back to Euclidean space. But they do the projection through like the correct mapping from a Riemannian manifold to Euclidean space. So there's like intelligent ways to do these projections. So basically, like if you imagine a sphere, you can project the problem to the surface, to like a tangent space that's tangent to the sphere at a particular point. And this is really common to do with manifolds because you can actually like work in manifold space really. And so basically they're just like doing this in a more intelligent way and doing like this smart mapping from Riemannian space to Euclidean space. And then they just solve the problem in the same way.
Okay, so you're saying like, it's similar to how people take a globe, like.
Yeah.
Countries and then map it to like.
Yeah. Actually, there's an interesting Wikipedia article when I was reading about geodesics that about how to like properly map the globe to a flat space. Like there are a few different ways you can do it that like kind of warp the size of countries
Like the
differently.
Country comparison, have you seen that website where it's like you look up a country and then you move it around the earth and it's like, here's how big the Congo is, like over the US. and
Okay.
you're like, it's like half the size of the US.
Interesting.
It's
I've never
fun to
seen
look
that.
at
Yeah, but it was basically about that like the way that you like unwrap a globe kind of scales everything. But yeah,
And so like
Right.
conceptually, they are just the formulating this planning like convex graph problem.
Yeah.
In these manifold space and develop the theory for it. But then once they develop in like the manifold space, they leverage existing projection techniques back into standard Euclidean space and
Yeah.
solve it. As opposed
Exactly.
to take the original problem and just kind of, it's like kind of doing the projection later.
Yeah.
As opposed to
I-
earlier on.
I think it's doing the projection kind of locally to each of the sets. And a good example of that is they solve this problem later on. I can jump ahead to yeah, I guess this is just results, but they're solving when they're actually solving the PR2 problem, they solve it in a couple different ways. First of all, using the algorithm that they propose here, where they're doing these like smart projections, and then they also solve it using the previous approach, but instead of doing anything intelligent, they just like for the joints, they just assume that the joints have to be between 0 and 2 pi radians. So, and then treat them as if they're in linear space. And then they also do another one where they just treat it as being between like negative infinity and infinity, where 0 and 2 pi are the same joint angle.
I see.
Yeah, so it's like, I guess doing this more like this better approximation of the set to, or better projection to Euclidean space.
Are distances preserved from these projections?
Yeah, so because so this is where the curvature of the manifold comes in. So if the original manifold is not curved, then distances are preserved and convexity is preserved. So that's kind of the whole reason why they can't do this in like SO3, which is the space of attitudes in 3 dimensions.
So like the top curve there, that
Yeah.
isn't like you had another image that was like the positive and the negative curvature, right? Like that
Yeah.
the original curve has to have no curvature, right? And so
Mm.
does the projection. It's
Like
just like
no curvature in, I guess like
they had those maps, psi have
Yeah.
to preserve distances in order for this to work.
yeah.
And so the distance on the top curves have to match up with the distances on the bottom one. But that wouldn't be the case if the geometry on the top, like, if
Yeah,
that,
if it, like,
if
warped
that
it.
mapping warps it, right?
Yeah, exactly.
Okay.
Yeah, so they also have this example of the surface of a cylinder, and this one you can kind of see is flat because you can just like unfold your cylinder. Like if you had a cylinder made of paper, you could just like unfold it and all the distances would remain like if you found the shortest distance on the surface of your cylinder and then unfolded your paper, it would be the same shortest distance.
So I also had a question on this.
Yeah.
So like in their like derivation, how do they optimize for the points of the like intersecting regions, right?
Yeah, so I think what they're doing, and they don't really address this earlier on, but I think each of the regions has an overlap, and that's where the like that's where the XU and XV have to live. So I
Oh.
think this space, like XE, is actually a subspace of 2 convex sets.
Okay, so they force their vertices to be in these overlapping regions.
Yeah.
and then they don't find vertices in the areas that aren't overlapping, right?
Correct.
Okay, that makes sense.
But the non-overlapping regions are convex, so
So they can do the mapping from an overlapping region to another overlapping region through a non-overlapping region.
yeah, exactly. Yeah. Yeah,
So,
so basically,
sorry.
yeah.
So like there has to be overlapping regions. You can't have like two maps that are like touching but not overlapping. Or like two regions, right?
yeah. So like they don't really address this in, I mean, I didn't read this paper in all that much detail, but they don't really address that here because like if you add in an overlapping region here, you'd have to add it in a particular way such that your sets remained convex. Like you couldn't grow Q1 into this region. So I don't know how they do that. But yeah, I guess they like do some growing of sets.
Okay, thank you.
Yeah.
Wait, so I'm confused because in section 6D, they're like you've been saying, like at this point we have shown that the flatness of Q is sufficient for our formulation's validity. It's natural to ask how central this is, especially since SO3 is really important for robotics. It has positive curvature. And then they show like if there's positive curvature, then the distance is non-convex. So I guess but then it still works because then they show like a toroidal experiment. So are they just like it's non-convex, but
I think
are they like what solver or like what optimization method are they using?
So I think they say at some point in the paper that they make these kind of bold claims because they want to have guarantees on the system. So I think probably in the toroid example, they're doing the same thing where they're projecting to Euclidean space, and then in Euclidean space they can solve the problem, and whether or not the problem is actually optimal, like globally optimal in the original solution space can't be determined, but it'll still give you a solution.
And it gives you a quick one, I guess.
Yeah, I think in the toroid space it was like less than 1 second to solve. Yeah, and so they say that so if all these conditions hold, that mainly that the space is non-curved, then the optimal problem that's solved in Euclidean space, so once you do this projection and solve the problem, it is actually the optimal solution on the manifold. So basically this transformation is lossless, which is kind of cool. But unfortunately a bit limited to just like angles, I guess. Yeah. And then this is just saying that even if there's just a single point of positive curvature, so if you just have like one angle, like one ball joint, then it kind of breaks apart the whole thing because now you kind of lose guarantees of convexity. But yeah, like Isaac said, I think you could probably still solve the problem and you maybe would do better than trajectory optimization still, but it wouldn't give you the same guarantees that they have in the paper. Yeah, and then they have a bunch of cool examples. This is a point robot in a toroid world. So this toroid like kind of wraps around.
It's like a donut.
Yeah. And so like this the black line kind of continues into here. Oh, they do address the overlapping regions here. The dotted lines here show like the overlap between regions. So that's, I guess, where the vertices are allowed to be. So like there's a vertex kind of in this, I guess, constrained to be in this dotted region. And then here the reds are obstacles. And they could solve this in 0.79 seconds, which is pretty cool. I don't know if that includes the time to determine what the convex subsets are.
So is the dashed line the vertex region, or is it just like showing the graph of the connectedness between regions, right? Because the dotted line goes through the red area, which I think is you're not allowed to have a vertex there.
Yeah, it says it's the region, the dashed lines indicate which regions overlap.
Right, so I
So I
think
guess,
that
yeah,
means-
these are the regions.
I think that means like it shows the graph, like you had in one of your slides, like it shows the graph of the connectedness between the regions, but like the dashed line itself
Oh, yeah, I
isn't
see.
the region where the vertices go,
Mhm.
but it shows like,
Yeah, it's like the graph.
Yeah, so I think like you're talking about the dash line through the red obstacle, the blue, so the blue, the long vertical one has some overlap with the
Yeah,
top
yeah.
yeah,
And with
one.
these.
Yeah.
Hard to see visually, but
Yeah,
I
that
think
makes sense.
those dash lines are
Right.
Yeah.
suggesting.
So I guess even in this plot, like,
Maybe
I guess you
see-
can see there's like a little bit of overlap between the sets, but
Oh, yeah.
it's hard to tell. And also, like, that's not where the vertices end up. Well, I guess this one looks like it's maybe in that region. Anyway, that's a good question about how they determine like the overlap. Because I feel like because you're forcing a node to be in that location, you'd lose some level of optimality by doing that if you didn't do it correctly. Yeah, so this was the mug reorganization problem that I was talking about. So they have one arm, and they have 3 shelves, 3 different colored mugs, and they're trying to place all the mugs of one color into the same shelf. And so they talk about how they have these regions that are defined by like shelf number 1, shelf number 2, and like kind of yeah, like more geometrically driven and like something that a person could write out. And they're able to solve this in 25 seconds per segment, with 14 segments. I don't know how that compares to like learning based methods. Maybe you guys know better, but you don't have to learn, so it's pretty quick.
And it also still takes 30 seconds for the robot to, I don't know if you've seen those like manipulation videos, but it takes, normally they're on like 8 times speed because it takes
Yeah.
for the arm to like do anything.
Is that just like for safety that you reduce
No, it
speeds,
just takes a
or
long time. Like
just
like
slow.
diffusion I mean, it's getting faster, way
Uh-huh.
faster now. But like when diffusion policy came out, like those videos were always on like 12 times speed because it's just like diffusion models take a really long time with images and stuff. So
Yeah.
But
So even inferencing is slower. It's the
inference
just that the
is-
trajectory it finds is okay.
Inference is slow.
I see.
So they use that.
Yeah, this is also nice because the trajectory it finds is optimal. Like it's globally optimal, so it will find a solution that can be solved as fast as possible. Yeah, and then they show this PR2 example, where they're trying to, I think they're also doing pick and place. And so they have this comparison of their algorithm with a few other algorithms. So their algorithm is this first column. The second one is just a trajectory optimization algorithm. The third one is a sampling-based algorithm. Then this one is a sampling-based algorithm to initialize a trajectory optimization algorithm. And then, like I said, this is the Euclidean space GCS planner with joint limits. So they say that the joints can only be between 0 and 2 pi. So that one's obviously going to be suboptimal because if the arm wants to go past 2 pi, it has to go like all the way back. And then same planner, but with no joint limits. So they just like do the mapping themselves. And then these are just different tasks. So this is like going from the top shelf to the bottom shelf. These are like crossing left, crossing right, and then middle. And if there is a cross out, it's because there was a collision. And so basically they show that their algorithm does pretty well. They also seem to be very generous to all of the other algorithms. Like they'll give them like better warm starts, and like they talk about how they kind of like assist all of these algorithms, which I thought was kind of interesting, but they still seem to do better in general than all of the other ones. They're a little bit,
They're not that much better than the last column, but
yeah. Yeah, and the last one, I think it's like a worst case and best case.
I see. So it's like
Um,
not always consistent. Yeah.
Yeah,
but also the last column is their last paper, right? So
yeah,
they
they
don't
can't
care.
completely trash it. Well, all of this is also like their work. Like this is Russ-Tetrick's trajectory optimization stuff. I don't know if this is from their lab, but so they're comparing it to like their own stuff. So I guess they don't want to like completely trash it, but it does do pretty well. Like
I'm surprised like PRM plus TraJopt is worse than the individual
Yeah.
methods. I would have
Yeah.
expected it to do better.
I would have thought it would be really slow, but better than the others.
You have to
But I guess, yeah,
like it'd either be the sum of the time. These are times, right? Oh,
these
no,
are
it's
trajectory lengths.
Oh.
Yeah,
So just-
yeah. But like you would think that it would.
Think of that.
I guess maybe it just found like a local minimum
Yeah.
that violated. Yeah, I don't know. And yeah, these are the times. So their method is slower than the rest, but I guess also results in less collisions and more optimality. So yeah, it's still pretty, yeah, still quite fast. And yeah, that is all I had.
Do they have a code base, or if you wanted to run this, we had to code it up? ourselves?
Yeah, no, they do have a code base. I think like it kind of exists as part of Drake.
What are you doing?
Yeah.
I think I remember trying it once and I was like, this is very opaque. It's kind of cool.
Yeah.
What's wrong
Cool
with it?
idea.
It's just, I mean, it's like,
Huge.
it's just big and it's like,
Oh.
I
The
have, no-
documentation leaves something to be desired.
yeah, the documentation was kind of weird. It was like kind of hard to tell.
There seems
I
to
don't
be,
know.
there's like many ways to do one thing.
I felt like Matplotlib kind
Mm.
of,
Okay.
which is like not. I don't know if that's really a compliment, but I just couldn't really tell what I was working with.
Yeah.
Yeah. Yeah, I tried to find the algorithm for breaking up the space into convex subspaces at one point, and it was like way too much code. I couldn't find like where that part of the code was.
I also, so if you're to do it like on a toroid or whatever remodeling manifold you're interested in, like I feel like that's kind of complicated. Like to, like, would you run like a computer vision algorithm, or I don't know how do you, like, if you wanted to automate that, like how
To automate what part?
the convex set dividing.
Oh, like you would have to have the environment mapped out before.
Yeah.
And yeah, like exactly. Yeah, like the partitioning step seems, to me, seems pretty non-trivial if you try to scale this up. Which
Yeah.
I don't like. I think it's an interesting problem. I don't think that's necessarily a bad thing, but I'd be curious how that
It's good that they don't mention it.
works.
Yeah. I guess like in some cases, like I'm thinking about like a ball joint, for example, you could probably go to like all angles except for like if you had like self collisions or something. So that would probably be pretty easy to represent that like some of your parameters couldn't be some subset of angles. But yeah, I don't know on a toroid how you would represent that.
Are you planning to use this in your work?
I've been trying to use some aspects. Like I said, I've been doing this multi-agent trajectory optimization work. So that was why I originally wanted to figure out how they separated their space into subspaces, because even doing that for like a simple example just requires me to write out a bunch of polytope definitions. And I don't know how I would do that for this without like taking way too long to do that. But yeah, definitely as a comparison at the very least. And I think this also kind of has some similarities to the consensus ADMM stuff that we're trying to do. But we're just trying to do it, I guess, as like a single non-convex optimization problem instead of using this like mixed integer approach.
Any other questions? Thank you very much.
Anubhav next week. I'm the week after, but I also can't do next week, just given L4DC. But maybe we could cancel next week.
Someone wants to.
I'm not saying
volunteer.
lost the ball.
I'm not gonna be here next week either.
Oh, yeah, no.
Cancel. Yeah, you guys, I know it's also like midterm season-ish, so. yeah, people have classes. Are there any more ACL folks to?